My name is Simon Pratt, and I'm here to present the Go assembler. And as I said, I'm going to start with a bit of a slide about myself. So first of all, I tend to talk really fast in presentations. So if that happens, just like I don't know, jump up and down, and shout or something, because I need to be told. I don't know this. I'm not very aware of it. Okay, so aside from that, I should also say that I'm not really a Go developer. I mean, I've been playing around with it since January, but up until yesterday I was really a Node developer. Before that I was a Python developer, and now, starting today, I'm like a Scala and C++ developer, so maybe related to Go, but sort of not really. Also, there's this really good talk by Rob Pike, and if you're interested in the bigger story of Go assembler, you should definitely check it out. It's about 20 minutes, but he goes into some really interesting details about why they did the things the way that they did. And it was just last year, so not a lot has changed since then. And also, he's just a really good speaker, so you should definitely check it out. Yeah, so I'm going to be talking a little bit about why they did the things the way they did, but if you want to know more about that, go here. Okay, so first a quick summary. So really what I'm going to be talking about is Go's compilation process. From what I've used Go, from my experience, it's just like you feed Go into this compiler and you get native code out. But that's not really the whole story. It's really compiling to this weird assembly language that doesn't really correspond to any actual computer, which is kind of neat. And it's using this as an intermediate representation, which a lot of compilers do, but this is the only one that's really it's modeled after an assembly language, so it's kind of neat. If like Luke, you're interested in lots of different languages. Okay, so Cameron actually asked me to include a bit about why you should care. I mean, I thought it was obvious, but maybe I should actually motivate this entire presentation. So I think in general it's useful to know what's going on underneath the layers of abstraction, sort of to know what the compiler is actually doing and not treating it like a black box. But in particular, there are some pretty good reasons why you might in particular want to know Go assembly. And one big reason is performance. If you want to get rid of some things like one of these blog articles I read got a bunch of performance gains just by getting rid of the bounds checking on arrays. And so if you are really, I don't know, performance limited, maybe that's a useful thing to do. Aside from that, debugging, there's a command, an option, I guess, to feed into the compiler to see the actual assembly output that it's generating. So maybe that could be useful in figuring out why something is breaking. And finally, you may want to use an instruction that's not generated by the compiler. The compiler doesn't necessarily generate all 1,000 or so of x86 64 instructions, and you might want to use something very specific, for encryption. As a little caveat, though, usually if it's not generated by the compiler, it's also not generated by the assembler, or it's not accepted by the assembler, because the assembler was really written to accept the compiler output. So that sort of makes sense. But apparently it's very easy to add an assembly instruction, if that's what you want to do. So it still may be useful to know the assembly to do this extra, to do these instructions that aren't generated. Okay. So the questions that I'm going to be trying to answer today, I'm going to give a quick intro to assembly, although it sounds like a lot of people have dealt with hardware before, so maybe that will be, maybe I'll skim that. Next up, I'll be looking at Go's assembly language in particular, why it looks this way, although Rob Pike covered that in more detail. In general, why do we want an intermediate representation? And do other language toolchains have intermediate representations? I think I already said yes, but I'll just give you a bit of context and comparison there. And I'll show you a running example thanks to this neat tool that the Golang people came up with, this present tool. I can run code in the slides, so that's going to be excited to use that. Anyway, but before we get there, what's assembly? So to answer that, I need to give just a little bit more clear model of what the computer actually is. So normally, like as a C developer, you would think of just the computer as like a sequence of memory addresses, and you don't really think about registers unless you're doing more advanced C stuff than I've ever done. But in reality, in addition to the memory, which is part of pretty much everybody's model of the computer, there are also these registers, which are usually very few. In particular, National 32532, which is very old CPU from the 80s, has 8 registers. x86-64 has more, but we don't care about that. We just care about this national programming language. But anyway, so that's important because the registers are where the actual work happens when you tell the CPU to do some instruction. You generally do that work inside of registers. Assembly language doesn't actually it doesn't really enforce this. You can't operate directly on addresses, but suffice it to say that under the covers things are happening inside of registers on an actual system. Yeah, and so then what a program is a sequence of bits that gets loaded into some special register, and then the CPU evaluates those bits, and then does the work that it corresponds to, whatever's encoded. And so for each of those instructions, there's a human readable version, and that's really what assembly is. So if we look down here, the binary encoding, it's kind of small. Oh no, I can't select to the side. Okay, it's the best I can do. So the binary encoding is a bunch of zeros and a 1, and like a bunch of zeros and 1s. And the assembly version of it is a little bit more readable, and I've also included the pseudocode. So what this code is actually doing is it's adding R1 and R0, which are registers, and taking the value that is their sum and assigning that to R0. So it's putting the value R1 plus R0 into the register R0. And what the assembly code for that looks like, in particular on the National 32532 computer, is add D, this isn't a typo, this is a double word, so 32 bits, add D, R1, R0, and it's implicit that you're going to be storing it in the second operand. So if that all makes sense, this is just the binary encoding. So assembly is this sort of human readable version of what the computer is actually reading and writing. So does that all make sense? Any questions?
Where did you pick the National 32532?
Yeah, so that wasn't random, and I'll get to that in like a slide or two.
Okay.
And that's good. Okay. So now an obvious question is, what does Go assembly actually look like? Now that we've seen this weird National 32K, I'll call it, assembly, what does Go assembly actually look like? So here's a little web app that I wrote. Hopefully it works. That takes Go code on the left. So let's say Go. So it takes some Go program on the left, and it will spit out the Go assembler code on the right. And really, this is just running some simple Go compile command with a specific switch and option on the execution. So it's not really doing anything special. And it's also going to take a while because I'm running it on Heroku. And Heroku, if your program doesn't get run all the time, it'll sort of archive it, and then when it gets run again, it'll bring it all back. And so that takes a little while. Oh no, it's a little off screen. What's that? Because I'm zoomed in? Yeah, it's because I'm zoomed in. Okay, so this is what Go assembly looks like. Most of this is just garbage. All of this stuff is garbage. But all the stuff to the right here is Go assembly code. So you can see this string gets loaded up here, go.string.below kw go meetup. The format println function gets called way down here. So all this stuff is just sort of stuff that you need to do, like loading things into memory addresses, loading memory addresses into registers and stuff like that. It's not really very interesting, but this is actually what it looks like. see a sub Q here, which is very similar to the add D that I showed on the previous slide. Except sub Q is subtraction, and Q is for a quad word, so 64 bits instead of 32 bits. So yeah, so it should look fairly similar to what I've already shown you. Okay. So the quick answer to why it looks this way is Plan 9, and also Ken Thompson, things like that, Bell Labs. But the longer answer is, in 1986, Ken Thompson wrote the C compiler for Plan 9, and he initially targeted the 32K architecture and expanded it to target a bunch of others as well. And the way that he did this was to generate a bunch of, he had the compiler just generate pseudocode that looked like the 32K, but then he could easily translate it to all the other architectures that they were supporting. And in fact, these assemblers that would take the pseudocode and translate it to machine-specific code were actually in the earliest versions of Go. It was replaced, I think in 1.5, they were replaced when they were getting rid of all the C code that was in the Go language. They actually finally had to take all the Plan 9 assemblers and throw them away and replace them with a Go assembler. And again, they didn't really want to change anything, so they stuck with this National 32K assembly pseudocode. So that's sort of why it exists. And it's worth noting that Plan 9 assemblers, there were a whole bunch of scripts that did almost the same thing. They were for one thing that would take assembly pseudocode and translate to 68K, for example, one for the 32K. But Ken Thompson and Rob Pike and whoever else were working on Golang, Russ Cox, I think, figured that they should sort of consolidate them and stop duplicating a whole bunch of logic. And so what they did was they just created one assembler, and it had a couple of environment variables that determined what the actual output was. And these are Goose and Gorch, and apparently those are the official ways of pronouncing those, FYI. And that's for Go operating system and Go architecture. Yeah. Okay. So that's why. So you may be interested now in why you might want an intermediate representation, but it's really for the same reason that Ken Thompson wrote his C compiler in that way in the first place. You want to generate one representation of the code that you can then optimize and then go to machine-specific stuff afterwards. And you've seen the Go assembler. It looks very much like actual assembler, so it's actually very simple to translate from Go assembler once it's been generated and optimized to whatever machine-specific assembly you have. Okay. So another question I wanted to answer is, do other language toolchains have similar things? The answer is yes. So GCC actually has 3 intermediate representations, generic, Gimple, and RTL. And the normal division is the front end will take C or C++ or whatever, Java if you want, generate generic, and then simplify that into Gimple, and then pass that off to the GCC backend. And the backend will actually take the Gimple and generate this weird language, RTL, internally to do more things before it actually spits out the native binary. LLVM is much simpler, and it's much closer in spirit to Go's assembler, although it doesn't really look like assembler, so it's not as cool. It takes C and C++ and generates this IR language, intermediate representation, is what it stands for. And I'll just give you a couple of examples of this, although all Go folks here are not super interested. So what the GCC front end generates is at first generates generic, which looks a lot like C, but instead of having blocks, you've got like an endif, so it's sort of like somewhere between C and bash. And then you work on that somewhat, and then you simplify it to a language that doesn't even have end-if statements. It's sort of like an if is a jump to one label or another. And that's what's happening here. If T2 is not equal to 0, Then we jump to L1, but if it is equal to 0, we jump to L2. So this is label 1, label 2. And you can also see that we're splitting up this, like all of these nested operations like A plus B, we're putting them into temporary variables, so there's nothing really nested in there anymore. This is a very simple language, and this is close to what assembly is kind of doing. It's like each line is a very simple instruction that corresponds pretty closely to one thing that a CPU could do. So that's pretty neat, and this is what the GCC backend takes. And what it does internally is it turns it into something that looks basically like this. But it's doing fairly simple things like set this register SI to 40, and then plus SI to this other stuff. So it's sort of like a Lisp representation of assembly. Yeah. Anyway, that's enough of GCC. On to LLVM. Where it's much simpler, we take C, something like return A times A, and we just split that up. We also do the temporary variable thing. So we multiply, we specify that it's a 32-bit integer, and we take A, so we're multiplying A by itself, and store that into a temporary, and then return it. So it's just splitting it up into simple one line. You'll also note, if you're very keen on it, that it starts as unsigned and it goes to I32. I think LLVM doesn't really have a concept in the internal representation of unsigned versus signed. It just has like, this is some number of bits, like 32 bits.
It must have like a sign extension operation then.
I guess so, yeah. It does something. Okay, makes sense? Fairly simple. Okay, so now the actual interesting stuff. So this is a working example, and maybe I should start with. So this is what's actually going to run. So I have a piece of Go code here that adds to whatever UX64 that you pass in. Super simple. We call it down here, but we also call add to as from the add to library, which is defined on the previous page. And it's going to do the exact same thing, but it's going to do it in assembly. So I can show you what that looks like. So here it is. You have to write this Go header file where you tell it what all the functions are that you're going to define. And then you don't actually have, I mean, these are just function declarations. You don't have to define anything. The actual code for this goes in a separate file, which has a .s extension, which is for assembly. And this is what the assembly code actually looks like. And it's fairly simple. It's doing the same thing. It's just adding 2 to whatever variable we pass in. So I'll just go over this pretty quickly. So this $0 here, dollar just denotes like a constant value. So this is the literal 0 value. And this refers to the stack space used, which is a little weird because we're going to be reading X from the stack. But this just tells us, it tells the Go assembler how much stack space we're going to be adding, like how many things we're going to put onto the stack, which we don't do at all. So that's why it's 0. And then we're going to move the quad word, so 64 bits, and this is the stack at the top position plus 0. So from the top of the stack, we're going to move whatever value is there into register R8. Why R8 and not R2 or whatever? Not really sure, but it seems to be convention to like start with R8. So I stuck with that. I saw somebody else use it and it seems to work, so that's all I can say. And then the next line, we're doing that add, instead of add D, we're doing add Q, so add quad word 64 bits. We're adding the literal value 2 to whatever's in R8 and storing that again implicitly in the second operand, so R8 again. And then finally, we're doing the inverse of this operation, except instead of moving it back to the stack, we're moving it to whatever the return address is, which is in ret. And then we're adding 8 because that's how many bytes it is. And then we're returning. that all make sense? So it's-
Regarding
Is the red address pointing like below the actual return value and you need to move it up or something like that?
Yeah, I guess so. This seems to be like red plus 8 is where it expects the no,
result, maybe.
no. I don't know. I mean, it works, so I don't really know why it's red plus 8. A lot of as when I was going through all of the documentation for this stuff, I would not say that it's very well documented.
My guess is, red is the address for the next return value. So for the previous return value, you have to jump backwards by the size of your value. But that's just a guess. So.
I mean, the caller had to leave all the space on the stack for these return values, right?
Yeah.
So you're just reaching to them. But, normally in assembly, you wouldn't even bother with that because you would just return it in a register to whatever other assembly or whatever, right?
Yeah, this is just some calling convention,
Yeah.
which I couldn't find. As I was saying, the articles that I read that talked about Go assembler, they pointed you at this one guide, which is not very comprehensive, and they said if you don't find it there, go back to the Plan 9 documentation, which also is not great. So basically, good luck.
Yep.
regarding R8 is not related to that joke in assembly programming that you should not use R0 because you will overuse the register.
Ah, see, you'll wear it out or something like that. That's funny. Okay, so let's see this working. I mean, it's not going to be very exciting. We're just going to print, add 3 to it, so the result of 3 plus 2 is 5. And if I wrote the assembly correctly, it should be the same thing. The result of 3 plus 2 is 5. So we run here. Perfect. It works. All right. Make sense? You have a rough idea of how this all works? Yep.
How do you generate assembly code?
How do you generate it? Like, if you've got Go code, how do you get the assembly out of it?
Yeah.
So I think that you add a -s extension, the capital S.
Similar to a SQL.
What's that?
Similar to like how you do it with a SQL.
Yeah, exactly. I think I could probably do this here. So if I did go to Go. Can't import Go. Great. Well, anyway, it should be -s like that. But it's not working right now. Go run hello.com works though. So I don't know what to do. Any of you know?
Do you need network access? Because it's trying to access GitHub access.
No, that's true. But I mean, that's this.
But it should be cached. in
That's
theory.
this package.
Oh, I
so-
see. Okay.
Anyway, any other questions? Yeah.
How come you don't have to save the contents of R8 before you offer it?
That's a good question. So,
Maybe consider like a register that's not expected to be persisted with the scratch register.
Maybe that's why they're making more interesting.
This
User,
probably
yeah.
don't use 0 through 7.
Yeah, probably.
Makes sense.
So call me save one.
The way to figure that out is that there should be some documentation on the
Yeah.
calling convention, so that's where it should be, but I couldn't find it.
So, do they assume? Are we at the question part yet? Or?
Yeah, this is
Do they assume that all of the processors they support are roughly the same in terms of like number of registers and like,
No,
which
so-
instructions use can do stuff with memory and which need and so forth?
No, so if you look at Rob Pike's talk, he actually shows you the output of the same code for a bunch of different architectures, and they. I mean, I guess that doesn't really answer your question. What you're asking is.
So do these actually map to the real registers, or does it do another? Does the machine-specific assembler do like actually allocate that to a real register? I
don't know, but I do know that it does. It doesn't. the instructions don't correspond directly, they could
Right.
map to whatever they want.
So I think with those intermediate languages like with LLVM and with GCC, the temporary variables it's using are just arbitrary,
Yeah.
and those may end up mapping to an actual register or to memory depending on what the optimizer decides to do.
Yeah, so I assume it'll do the same thing.
Because that stuff looks a lot like an ARM processor, which looks nothing like an 8086. And the ARM sort of has, the registers are almost all the same use-wise, where the 8086, you have specific registers for like I/O, like the DX register or whatever, or to address the stack space, you always use BP or SP. But
Any other questions?
So have you found any like sizable projects or people written a whole active Go assembly language, or is it kind of a curiosity of this?
So there was that one I mentioned that was getting other performance gains from getting rid of bounds checking. They actually wrote a really neat article for to Go assembly programming. But they thought they were, so what the whole article was just trying to optimize a divide by 3. And they wrote like a whole bunch of assembly code and figured out how to do it, and they were getting some performance gains. But at the end, or I think it starts in the beginning, they say, it turns out all of our performance gains came from not optimizing this divide by 3 to be some shift or something, but from getting rid of bounds checking. Because apparently it's very common for compilers to optimize weird divisions by doing Montgomery division instead, which is a pretty neat concept. I just learned about it here. So division by 3 is equivalent to, for like a fixed integer size, is equivalent to multiplying by this weird integer here. You get exactly the same thing. So that's kind of cool. So yes, they wrote a lot of assembly in their project, but it didn't end up being particularly important. But there is this other one, SIMD optimization in Go, that also talks about Go assembly. I don't know if there's a big project. I assume there's a project associated with this blog article. But I mainly skimmed it just to see what they were doing and how they got it to work. So, yeah, so at least a few people are using it. Any other questions? Comments? Corrections?
Can you bring back the references?
Sure.
If you can comment on them.
that code actually looks like 8086 because they got BX and BP and stuff all there, right? But no more R0, R1 or whatever, which looks like ARM.
Yeah, I think they're.
Seem too many different languages to remember anymore.
So I think I read that x86-64 has like aliases for like AX and BX, which are just R0, R1, etc. So you can use either in x86-64 in particular.
Okay, yeah, but the 64.
Exactly. Yeah. Anyway, you wanted the references?
Yeah.
And here, I uploaded. I sent this link to my GitHub account. It should be on the meetup page. So if you're interested in anything in here, I tried to have a reference for everything. So if you want to go into more detail, feel free. Yep.
Anyone try to use SQL and then assembly at the same time?
I don't know.
So what's the story with Plan 9?
It was supposed to be a better Unix. I guess it wasn't.
Also, because they worked at that Multics, yeah, like very big, and yeah, where they came up with all these ideas for the Unix, yeah, actually.
Yeah, well, I seem to remember Multics was never finished because they kept on adding requirements to it until it collapsed on its own weight of documentation and code. But I think Plan 9 affected like a few different operating systems like Herd, but for the most part, a lot of them have kind of taken like side and not very popular because of this Linus guy who back in the early 90s decided to release a free operating system.
Right. I think I've heard of ProcFS, I think. If you go into a recent Linux distro, if you can go /proc, there's like a whole bunch of information about processes that are running. I think that comes from Plan 9. I could be mistaken, but I think so. I think that the main idea behind Plan 9 is like everything's a file, and so this proc file system is every process is a file, every piece of information about a process is a file. So, but that's memory from my operating systems course I took many years ago.
Yeah.
So it went kind of a parallel development with Unix till Linux came up, yeah, kind of.
I guess so. I know they were working on it in 1986, which is when they did this. Anything else?
And it might be back in a few years after Linux collapses under its own weight,
Right.
as some of the kernel developers have been predicting, apparently, being a mega kernel.
Yeah, after Linus retires.
That too.
Yeah, Minix is still alive and well, yeah. The Tannenbaum initial microkernel idea, yeah. So there is an article in Communication at ACM last year in March where Tannenbaum talks about it was 30 years anniversary of Minix, yeah. And he still pushes like a future operating system because of the microkernel architecture, yeah. That what QNX has a microkernel too, yeah.
So it's Herd.
Yeah.
Yep.
So we don't know what the future holds.
So Linux has everything compiled into the kernel, which is one big binary blob that runs at run 0. And by everything, I mean network drivers, file system drivers, memory management, everything under the sun. A microkernel, they basically cram or they throw everything out until you can just the very, very, very minimum of need that runs ring 0. And everything else is usually like ring 1 or ring 2 or the app level, which is been there. So, and this is using Intel maybe, but so the kernel itself contains interprocess messaging, only the very basic level. If you need longer streams and stuff, that's usually implemented possibly by a higher level facility. And some simple memory management, but not advanced. So because you can't do paging because you don't have any files for file systems or block devices. So because those are all optional drivers that can get stopped and started at any time, depending on your equipment. Of course, anyone who's experienced in any sort of CS knows that the startup and teardown of a program are the most complicated parts of it. But once you get the system up into a stable state, it's usually well understood what's happening. But that means if you have this fantasy of being able to, like say your network driver crashes, to tear it down and bring it back up again, it might be able to happen.
You're pretty much rebooting anyways.
But usually, what that means is you have a bunch of things that depend on that, and what do you do with them? Do you put the logic in there to, drop it and re-request it, or do you tear them down too? So then you end up with large parts of the system having to be torn down in order and then brought back up in a particular order.
Or you make them all wait because they call something that hasn't been restarted yet or something, right?
Well, that's the one of the two options. You can either have them like wait and retry or something, but the address might change. Or something.
So the microkernel is safer if you want to isolate GDI calls or whatever from crashing the system or doing things that people do these days to take over.
And the good thing is if somebody attacks your network driver, which is a common thing to do these days, then it's not going to compromise your file systems and the rest of your operating system because it's very guarded what you can get in between each of those areas. Whereas in Linux, good luck. It's free and open range if you get to overwrite one of the buffers.
Network used to write network drivers all the time. Never thought about being able to compromise them.
Exactly, that's the problem.
So how do people do that? Because they're throwing wild parameters at it and they're not people who wrote the driver don't check them.
Yeah, exactly. But one of the more recent famous exploits was, I can't remember what part of the stack it was, but you basically give it a packet, you say, yes, there are 5 parameters here, you give it 4. Or something like that. Or you do the reverse or something. And then it's like, basically it reads up to the end and then it reads a bunch beyond and who knows what it's now doing and or accessing, and then sometimes they just want to copy bits of that out into the memory that they can access and hope it's some little goodie, and other times if you can stack smash in a nice, or not a nice way, but in a very particular way, you can actually overwrite like your return address and have it then return to a section of your stack which contains code that was injected by the packet. Yeah.
So it also has the network driver is written in C because an assembler network driver, they would probably take all the parameters and registers and it wouldn't matter because you wouldn't be able to do that kind of thing.
Of course, everything's written in C. And if it was written in Go, they'd have bounce checking.
If you
Almost disable it.
You can't pass one less parameter in registers, you're just going to be passing whatever happened to be in that register, and then the program's going to say, well, whatever, that's a bad thing.
The network drivers are hugely complicated. Like, existing ones might take like a megabyte of code at the bare minimum these days, possibly 50 to 100 megs, depending on the network.
No, okay, not just
3G,
to send
4G.
a packet, but to
No,
do
like 3G, 4G, 5G, brutal. Wi-Fi, less brutal, but still pretty bad.
The reason for monoliths is speed, yeah? Because with the microkernel, if you are passing messages, you have to parse them, so, but with the monolith, you do a function call, so you get
Context
speed.
switches do kill you a little bit. I can't remember the exact stats from QNX, but I'm pretty sure on the ARM processors that we're using, it was running at either 93 or 97% the speed of a megakernel. So you're somewhere between 3 and 7% overhead. Sometimes that's significant. Other times you want safety.
Yeah.
And realistically, for most apps, it's not going to kill you. If you're running a server farm with 1,000 computers in it, or not 100,000 computers in it, 7% means you need to add another 7,000 computers. That's a lot of cash, so you may not want to do it.
So next month's plans are a little bit up in the air, but I believe it'll be June 13th, which is a Tuesday. But yeah, I should hopefully within a week or so have that posted.
Michaelton Ridge?
Possibly. Probably 10 reach. A little bit up in the air as well. Originally, Danny was going to present here person who helps out with arrangements and stuff